So we kind of ended on this other day. So the last thing we worked on was the 5 ways to calculate delta H. And hopefully all of that made sense. And again, we'll kind of hit those refreshers at a later date to kind of make sure that we're on the same page. So a lot of these things that we're going to cover today hopefully should go fast. Don't let me overtalk myself because I can on some of this stuff. But a lot of this is basics that you already know. So the summary for enthalpy. Again, what's the letter for enthalpy? H, and if it's positive, you know it's endothermic. If it's negative, it's exothermic. There is one thing that I want you to add to both of these, that if it's positive, you can write it beside this. I'm just going to kind of make the note up here, that heat is a blank. If it's delta H positive, it's endothermic. What is heat? It is a reactant. Very good. And I want you to add the exact same statement for the bottom one. You can put it underneath it. If delta H is negative, that means it's exo. Then heat is a what? It is a product. Okay. And again, please be very careful with how they list some of these things, because sometimes they're in the reaction and sometimes they're, I'll go back. Sometimes they are outside of it. So they'll just say delta H equals blank. And you got to figure that out based on where the heat is supposed to be, based on what they tell you. Okay. All right. So the next one. Help me up here. What does that say? Speaking of bond energies, allow us to clear up some common misconceptions and make some dazzling connections. I like that word, right? Dazzling connections. I copied and pasted that. That's not my word. Let's start with the vocabulary used to describe phase changes. So let's start right here. Number 1. What is a phase change? Solid to liquid to gas. My first question to you is physical change or chemical change? Physical change. Very good. That's going to be important. Okay. Totally just misspelled that. So we've got a physical change, which means whenever it changes states of matter, is it still that thing? Yes. Okay. So we're not having any chemical reactions here. First, you must realize the vocabulary is directional, hence the arrows on this diagram. We'll see in just a second. You'll have to mean what you say and say what you mean when answering free response questions, because here's people can talk themselves out of points just because they don't know what they're talking about. Number 1, when things begin to change phases, are bonds breaking? No. What's separating? Forces. So you have phase transition involving overcoming intermolecular attractions, or IMF, which again should never, ever, ever be confused with covalent or ionic bonding, because when it's a phase change, water is still water no matter what state it's in. You're only putting them you're either making them closer together or you're getting them farther apart. So things such as fusion, vaporization, and sublimation. So let's start with those individually. Melting. What is it going from and to? All right. Did you say metal? So, well, it helps if you would not do calculus in the middle of this. All right. Vaporization. What's happening? Liquid to gas. And then sublimation is solid to gas. So in all 3 of those different things that are occurring, are they getting closer together or are they getting farther apart? Getting farther apart. If I want to take something and make it get farther from something else, so what do you have to do with energy? Think about karate. Put it in. Chop it, right? Put energy in. We got to chop it. So it requires an input of energy to overcome the attractive force between the particles, substances. Notice, we did not speak of breaking bonds in this case. Freezing. What's happening in freezing? Okay, all right, so we've got liquid to solid. Condensation, we're going from gas to a liquid. And deposition. Very good. Gas to a solid. So all those things are getting closer together, farther apart. Closer together. Now, again, are bonds being formed? Say no. No. What's being forces? What's being formed? Forces. Okay. So when forces are made, energy is released. So again, kind of keep that in that state of mind. So we can talk about exo and endo in those 2 terms. So when we look at this is just kind of one of those mental maps that you can kind of create in your head. So you got from solid to liquid to gas. Again, the one thing that I want you to notice is this right here. The enthalpy of the system. Which system has the most energy inside of it? Gases. Why? They're what? They're moving. Very good. They have a lot of kinetic energy based on their particle motion. There's also one other word that we're going to get to in the next few slides that we can add to the side of this. What else also increases as you go from solid to liquid to gas? Very good. Add that in. Okay, so we're all, well, that's not the right thing. And, wow, thank you. Okay, and entropy. Mary, what is entropy? No. Yep, what is entropy? I'm talking to Mary. Mary Fabrini, what is entropy? I know that. What is it? It's disorder. What does disorder mean? It's the arrangement of the molecules. It's where I'm wanting you to go with that. So again, we know that gas is going to be the most. Now, the differences between a gas and a vapor, because we see this all the time, and hopefully by this point you know what this means. Yes, it is primarily semantics. And what is semantics? That is anthropology. Yeah, you're my bad. Sociology. I've been talking about anthropology and forensics, so it is sociology. No, semantics is basically wordplay. It's saying the right thing and meaning it in two different ways. So a gas is a gas at room temperature. We don't speak of oxygen vapor, right? Devin, give me something that has vapor behind it. No. Water vapor. Thank you. But rather, we speak of oxygen gas. However, we use the term vapor when the substance is, and here's the difference. When it's normally a liquid or a solid at room temperature, what is water normally at? It's a liquid, but it can be converted into the gas phase, right? So it's going to be a water vapor. Iodine, what color is it up there on the wall? No. It's black, okay? So iodine is normally what? Say the matter. It's normally a solid, but it actually goes through sublimation, which is what? Solid to gas. So when it becomes a gaseous state of matter, we don't call it iodine gas, we call it iodine vapor. Okay? Same. So we'd say water vapor, gasoline vapor, or iodine vapor. It would not make sense to say gasoline gas. Okay? It's a gasoline vapor. Sir. It is sublimizing, yes. Because let me think about the best way to say this. The boiling point and the melting point are so substantially close that when you introduce them to a room temperature, that it goes from the solid point to the boiling point instantly. Does that make sense? So it's going from its frozen point to above its boiling point. It's one of those things you just can't make. Nature is what it is. You can't really change it. No, you have to. The temperature has to be low enough to make it freeze. I mean, we're breathing out carbon dioxide right now. If it were cold enough, what you blew out could actually solidify, which is weird, but it could. Could we? Yeah, we're like 95% water. Absolutely. We can definitely just kind of boil ourselves. I wouldn't do it, but you could. Could you what? Could you liquefy it? Yeah, but it would have to be a slow change to increase the temperature to the point where it liquefied. Yeah, it's a very finite point. Yeah, they know what the melting point of dry ice is. I just don't know what it is. I know that room temperature, guys. Y'all stop. Okay, I know that dry ice's boiling temperature is room temperature. Okay. All right, so be very, very clear that changes in the phase of all matter involve altering IMFs and not altering chemical bonds. Now, this is one other thing, and we're going to get into this very much in the next few chapters, is how molecular properties are set up. And the whole key, and I want you to write this underneath this last bullet down here if you've got enough room, and it's okay. What is BP and MP? Boiling point and melting point. Okay, these are very dependent on strengths of IMF. Okay, so in the video that you guys watched this weekend, one of the questions was talking about boiling points and melting points, correctly? And what was the major thing that determined the differences in the melting point and boiling point? The IMFs. And if one was polar and one was non-polar, which one had the higher melting and boiling point? The polar one, because they have stronger intermolecular forces, right? That whole video and that whole question was based around that idea and that concept. Yes, sir. Okay. No, it showed the organic structure. It was pyridine and benzene. It was this one. Oh, it was the dimethyl ether and ethanol. You sure? You had to actually draw the structures? Okay, ZXO3? XE03? What was the shape? I don't even remember what the shape of it was. This? Okay. You got to remember that the problem with this, whenever you draw this, what dimension did I just draw this in? I drew it in 2D. But this now, it makes it three-dimensional, right? So technically, actually, this is it. Okay? What does that clear peg represent? That clear peg. It represents the electron pair. So you got to remember that if that black sphere, which is the xenon in this case, was being pulled in three different directions, the first thing you got to remember is those three green at the bottom are actually going to be pulling it downward and away from each other. But the problem is these pairs of electrons are actually going to be pushing all of these oxygens away from them. So because there's not an equal symmetrical pull on the xenon, it becomes polar. Does that help? Seeing it three-dimensional is much easier to understand it. Well, if it were two oxygens, it would change the shape. And I don't necessarily know how it would. I couldn't. Yes, but it would also. It would actually have to be charged if you took two oxygen, or if you took an oxygen off. Does that answer your question? Okay. You're gonna be playing with that the whole time now, aren't you? I understand. Generally, the more polar the molecule is, the stronger the attractive force. Now, of the three IMFs, which one has the strongest polar force? Hydrogen bonding. So that's why water's boiling point, that's why water's melting point is so extremely high. Hence, more polar molecules typically require more energy to overcome IMFs and is an endothermic type of thing. So phase transition involve the breaking or forming of IMFs. Hence, as with all other chemical reactions, it is necessary to discuss the energy that is absorbed or given off during the breaking or forming of IMFs. So the biggest key difference here is that when we're talking about phase changes, it's a physical change. When you're talking about chemical changes, what's being broken in that case? Bonds, and the two types of bonds are ionic and covalent. So you have to pay very much attention to what's going on. Now, these are phase change diagrams. Now, the one interesting thing about this particular topic is that these questions are no longer on the actual test, but it makes a lot of stuff make sense when you just look at what's going on. There's a lot going on in this picture. There's a lot going on. But the first thing that you always start with graphs, and even on the ACT, it's important that you start with this. If you start, that's not what I want. If you start with, so let's make this smaller now. If you start with the X and the Y-axis, as you go up the Y-axis, what's increasing? Your temperature, which means all molecules have greater what at that as it goes up? And kinetic energy. Okay? So you've got temperature increasing, therefore your speed is increasing, therefore your kinetic energy is increasing. All those things are going on. And notice what you're changing. You're going from solids to liquids to what? To gases. And look at all those particles. What are they doing from each other? They're getting farther and farther apart. However, is it still the exact same substance? Yes, you're just adding more energy to it. Now notice, as you move across from left to right across the x-axis, what is also increasing? the heat energy. Okay, so all these things have different energies. So the crazy part about it is there is so much going on in this one picture, but it explains all of it. So if you go from a solid to a liquid, what's occurring? It melts. Okay, and then you go up from a liquid to a gas. It boils. But notice what's happening. At all of the flat lines, and here's what I want you to write. Somewhere in here, the flat lines are phase changes. But here's the crazy part about this graph that a lot of people overlook. Focus on the melting part. And I'm going to highlight it in purple. This square purple box. What is the slope of that line? 0. Therefore, what is the temperature change the entire time that substance is melting? 0. But is the energy changing? So the temperature's not changing, but the energy is. So how can you have all these things with no temperature change? But say it again. You've got a lot of things going on. So you've got all of these molecules that are starting to separate distance-wise. So what happens whenever molecules begin to separate? That's true. We'll say it's a closed container. When molecules separate and they begin to move, you've got more energy because they're running into each other. Because you've got more molecules running into each other. So notice what happens. Even though that the temperature stays constant, you're constantly gaining energy. So is there ever a point at which the energy stops increasing? No, it's going to constantly increase, even though the temperature maintains itself. Also, this is another thing. At a phase change, which is PC, I would definitely write this down because when we get into this, we're going to definitely have to know that. At a phase change, you are technically at equilibrium. And again, what is equilibrium? By definition, it's a constant rate. So the same amount going forward, you have the going backwards. So right here at this, again, this purple box, in this entire time that it's flat, what's happening at that flat line? The same number of molecules that are turning into a liquid are also doing what? Turning back into a solid. And so it just takes a certain amount of energy to get it to finally overcome this point where they all become liquids. Okay? And so that's kind of what's going on. And you can look at it from any points. You can also take it and look at it from this perspective. What's going on during that entire flat line? Equilibrium is. It's either boiling or it's condensing. It depends on which way you're looking at it. But all of those things are going to be going on that entire time. But is the energy constantly increasing as you go from a liquid to a gas? Yes, because they're starting to run into each other enough where they can separate to a certain point. Okay? Help me with that first top line, please. Okay. All right, so you're going to have to answer some of these questions, okay, because y'all don't have the answers. Does the process above represent a collection of chemical changes, physical changes, or both? So put PC, physical changes. Okay. Everything that you just looked at with water, it was all physical changes. What type of force is involved in the changes you identified in question 1? IMFs, intermolecular forces. There's one thing that I want to kind of throw this at you real quick. Is there a difference between intermolecular forces and intramolecular forces? What does inter mean? And see, that's the problem, is between molecules. What is an intramolecular force? That's within the molecule. So, if we go back to this example right here. Let me take all this purple off. This right here, in that yellow circle, is a singular what? That's a single. What is this thing called inside the yellow circle? That's a single molecule. Can I make this molecule link up and stick to another one? All right, I'm just gonna draw another yellow circle. I'm not gonna fill it in. But if we link these two, what would those purple dots represent? Which IMF? Inter or intra? Inter. Why is it inter? It's because it's between. Now, we've always called these lines what? We've always called them bonds. But some people refer to them as another type of IMF. And it's not inter, it's what? Intra. Because intra means within the molecule itself. So that's what all of those lines would become. Now, I prefer the term bonds and intermolecular forces because it would be easy to confuse intramolecular versus intermolecular. Just throwing this at you. This XCO3, is this polar or nonpolar? This is polar. My second question is, if we're talking in terms of intermolecular forces, IMFs, which one can it obviously and easily not be? Why can it not be hydrogen bonding? There is no hydrogen, so that eliminates one of them. Since it's polar, that then makes it what? Dipole. Yes? No? Okay. Hopefully that's easy enough. All right. Define the temperature. The average kinetic energy. So average AVG KE. AVG period KE. Average kinetic energy. Which conversions involve temperature changes? All changes. I know, but all conversions involve temperature changes. Okay. Which mathematical formula for calculating the energy associated with the process you identified in question 4? What formula is that? Q equals mCp delta T. That specific heat formula. Okay. Because you got to remember, is there a specific amount of energy required to change a substance? Yes, and that's what specific heat is. Okay. And then which conversions have potential energy changes? All of them. All of them. Freezing, melting, condensing, boiling, vaporizing. All those are opposites of each other. Now, I think the reason that this is so difficult is, again, mentally being able to look at something and decipher if it is a chemical change occurring or a physical change occurring, because all of this can be so drastically different. When calculating, what does that say? The appropriate... Nix that one. Let's move on to 8. How do you calculate Q for the process identified? Number 6. Nix that one as well. Which portions of the graph are represented at equilibrium conditions? So when will you have equilibrium? Right here. This white word. When it plateaus, which means what? When it flattens out, when it's flat. Okay. Another way you can symbolize that is that delta T equals what? 0. That's another way I would write that. You can say flat lines, you can say plateaus, and you can say delta T equals 0. Because if the temperature's not changing, is the energy still able to change? Yes, which is strange and odd, but that is changing. Okay. Potential energy is added to overcome the IMS, blah, 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 blah. All right, so completely getting into the new thing, and we've already talked about a lot of this. So what drives a reaction to be spontaneous? Remember, when we talk about spontaneous, we no longer use that term. What do we use? Thermodynamically favorable. And again, there's only 3 letters that tell you if something is truly thermodynamically favorable or not. That is what? G, E, and K. Within G, you've got 2 other factors. You've got delta H, and you've got delta S. And as we saw in that worksheet that we did, is it possible for H or S to be non-thermodynamic, but G to be thermodynamic? Yes, and we're going to have to figure that out. But what happens when both H and S are both non-thermodynamically favorable, which means it's endothermic and it's becoming more organized? Then G is definitely going to be non-thermodynamic, right? Okay. What if both of them, which means it's exo and it's becoming more spontaneous? What happens to G? If both are thermo, then G is. If neither are thermo, then neither is G. But what happens if they're opposite? We'll get into that. We'll figure out exactly how we can do that. All right, y'all know this. Can move on. Thermodynamic favored process of reaction are those that involve both the decrease in internal energy of the components. Now, when it says, how this is worded is very, very crucial. A decrease in internal energy. That means where's all the energy going? Out. If you're decreasing your internal energy, it has to go somewhere, right? It has to go out. Well, what type of reactions get their energy out? Is that not what delta H wants? It wants to be exothermic. And an increase in entropy. So it's releasing all this energy, and what's it doing? It's making things go crazy, okay, which is positive delta S. These processes aren't necessarily thermodynamically favorable if delta G is not negative. Again, you can have both, or you can have one of them be and the other one not be, and delta G still could be positive. So, if you're using an older textbook, you may see these reactions referred to as spontaneous. Again, we are now thermodynamically favorable in terms of how we're going to say it. What is that stuff in green? What is? Yeah. The amount of energy required to start a reaction. I know what you're talking about. Okay. So, if I want to label above that dash line, the top dash line, what is the from here to here called? All right, so this is our EA. What is from here to here? Okay, remember this guy? What was his law? The sum of the delta H of the products minus the sum of the delta H of the reactants. So let me ask you something. If the reactant value starts right here, change colors. If it starts right here, and the product ends right there, how do you find delta H? Take the difference of them, right? Is that this law is right here, just in graphical representation. So these two things are 100% identical. Your brain just has to figure out that, okay, I'm just doing products minus reactants. If you were to do the graph that I have drawn, what is the sign of delta H of the reaction? What's the sign of it? How do you know that this is going to be negative? Do you end with more, or do you end with less energy that you started with? You end with less. So what is the sign of less energy? Negative. The other way that I taught you to cheat, draw a slope. What is the sign of the slope of that green line? Negative. Well, that automatically tells you what's going on. Okay, that's the cheat way to do it. Then you can do the calculations. Well, what happens when you flip this graph over and you now have an endothermic graph? Okay, again, we still have reactants, we still have products. So, you want to see the crazy thing about this one? What is that red line? Very good. What is the orange line? It's delta H. So what do you notice about the delta H versus the activation energy comparison? You have to put in more energy than you're even going to get out to make it work. Would nature prefer you utilizing this much energy? No, it's a waste of its time. Because look at the net gain. You're having to put so much energy in, and you're not going to get a whole lot out of it. So that's why that most endothermic reactions do not happen unless you've got some sort of outside force acting upon it, which is exactly what this says. Thermodynamically favorable processes occur without outside intervention when? Read the blue. Once the activation energy has been reached. And so once you overcome that, it's just going to keep right on trucking. The thermodynamic does not predict nor take into account the rate of reaction. Guys, do me a favor. And I know it's hard to see these in different colors, but these words need to be connected. The rate is going to be kinetics, and that's the next chapter we're going to get to. Everybody, to me, y'all enjoyed electro, right? Was it bad? Kinetics is even better than electro. People like kinetics the most. 100%. Every year, people do the best on kinetics. Well, we're not talking about that. You're not going to fail it. Okay. So here's the deal. Do some things burn really fast and some things burn really slow, right? However, are they burning? Yes. So when we talk about kinetics, we're going to talk about how fast it happens. When we talk about thermo, we're simply talking about this graph. The only thing that we're focusing on is this number right here in this green circle. Everything else we could care less about. We're not focusing on if this were time, right? Because could you take two different reactions, and I'm going to flip this around. I'm going to draw two graphs. Okay? Could some reactions happen like this? Is that really fast or really slow? Really fast. Some reactions could go on forever. But bottom line, what if their delta H's were the same? That's what thermo focus on. How much energy differentiation is there going to be? Kinetics then focuses on how long did it take to do those things. So the combustion of hydrogen, is that really fast or really slow? Really fast. But what about graphite turning into diamond? It's extremely slow, but it can happen, right? Does that happen? Does graphite turn into diamond? Anybody have diamonds? You will one day. Okay. Whatever. Go ahead, Nick. Go ahead. Question. Okay. All right. I'm going to tell you this now. You need to know both of these by explicitly, because you're going to see it on the multiple choice part. You need to know the first law of thermodynamics. That one's easy. Energy can never be created nor destroyed, but what? It only changes forms. The second law you may or may not know, and I'm telling you now, you're going to have to know this. Say it again. Who? I don't know. Philip. Yep. Okay. The entropy of the universe increases in a spontaneous process and remains unchanged in equilibrium. So what they're telling you is that what does the universe prefer about its delta S? It loves it very, very, very high. It loves positive numbers. But here's the crazy part. If it is ever at equilibrium, what is your delta S? 0. So anytime you are at a phase change, what are you also at? Equilibrium. What is your delta S? 0, because there is not a difference in changes of states. So everything in terms of the entropy value will be the exact same. Okay? Now, this is the last one. This is the third law of thermodynamics, and this is the one that makes the most sense. You guys tell me, whenever we were solving for Hess's law, with using the table numbers, is it possible for delta H to ever be 0? From the table, can a compound have a delta H of 0? When was it 0? When it's in its normal, regular, natural, standard state, right? Now, that's for delta H's. Let me ask you this. What does delta S mean again? Entropy. Think about this. Can a molecule have 0 entropy? Can anything ever be completely and totally non-chaotic? Why not? I agree with that, but how can you make something have no disorder? Absolute zero. What is absolute zero? Zero K. But what does that mean? What is everything stops? Even what part of the atom specifically? The electrons stop moving. Have we reached that point on this planet? No. So what you just told me is the only way to have something have no disorder is to put it at absolute zero. However, is there anything on this planet at absolute zero? No. So can we have a zero for entropy? No. So this is what this says. The entropy of a perfect crystal at 0 Kelvin. We need to stop right here. The first thing is this word. Perfect crystal. Possible or not possible? Not possible. Kinda. That's a good question. Everything geometrically lines up perfect. There's no strays or issues. Try to buy one of those perfect diamonds and see if your bank account can afford it. Okay? All right, 0 Kelvin. Absolute zero. So far, we're not even all the way through this thing, and we've got two things that do not exist on this planet. Things such as perfect crystals and absolute zero. Neither of those two things are real. So then it says the entropy of a perfect crystal at 0 degrees Kelvin is zero, which means the delta S of that thing, whatever it is, would be zero. So there's not a lot of perfect crystals out there, so the entropy values are rarely, and I will go ahead and tell you, are never going to be zero. But if there's ever a question of hypothetics, that would be the only case. So what? Go ahead. Your question? Okay. This means the absolute entropy of a substance can then be determined at any temperature higher than 0 Kelvin. Again, we don't even have 0 Kelvin, so everything has to have it. Handy to know if you ever need to defend why delta G and H for elements are 0, but entropy does not ever equal 0. Again, two possible situations that do not exist because of kinetic energy and temperature. We can't get those yet. That is going to change all the laws of chemistry if we ever hit it. I don't really know, to be honest with you. Okay. So, the entropy of a perfect crystal at 0 degrees Kelvin is 0. So, which one of these up here would be perfect? The one on the left. Again, if you notice, there are some weird, strange things going on over there on the right. Now, what are all those little peanut-shaped looking things? Or a teardrop? Okay, they're compounds. They're molecules stuck in a crystal lattice, right? Because that's how ionic compounds are done. And there's some differences in the reason why these things move. And here's the interesting part, and I think it's this slide, right? I promise I'll come back. I'm looking for something. Hopefully it's in here. This is it. Water. If we took water, Mary, and we froze it, Nick, what if we got it as close to absolute zero as possible? Could a water molecule still move? If it's as close to absolute zero, not absolute. If it's now, so here's what you need to understand. Molecules, atoms, and electrons have two different types of movement. One's in green, one's in yellow. One of them is rotational, and one of them is vibrational. Okay, so let's look at the difference. What does rotation mean? Rotating. Okay, how many of y'all like those rides at the fair where like your thing spins, the whole thing spins, and then the entire whole thingy is spinning? That's like the disco dance or something. What's that called? Not the zipper. There was like you sit in the thing and it rolls upside down, but the whole time it's rolling, like it's doing a 360, and then the whole entire something like that. Yeah. So you've got all of those things going on. You've got rotational. You've also got vibrational, and here's what vibrational is. It's basically, do you agree that what are these black lines representing? No, these are the bonds. And what happens is you have three different vibrations. Stay with me, guys. They can actually bounce away from oxygen. They can bounce towards and away from each other. And they can bounce away and towards. So it's kind of like if you took a big slinky. You can make a slinky go in all kind of different directions, right? You can make it go up and down. You can make it go side to side. You can create waves and all of these things. So when you took physics, y'all did a lot of physics waves, right? This is what all of that was. This was all rotational and vibrational energy that you guys were studying. Okay, and so that's the two different types of ways that things can move. Well, if all of that rotation and vibration stops, what happens to the molecule? It stops moving. Those two things we've never been able to stop all of them. All right, so kind of coming back and looking at where we stopped. This right here. Again, we are only focused at here and here. We're only focused on the outside of that. That is delta H, delta S, and delta G. What is the inside of all of this? From here to here is kinetics. And again, what is kinetics? How fast it happens. We'll get to kinetics in the next chapter. Okay? So what is entropy? It is difficult to narrow this concept down to a single definition, but let's try it anyway. Here's a little bit different view. And I don't like this. It doesn't work for me. However, it's like I've told you guys several times. My job is not to teach you what I know, is to teach you what you can learn. And so this is a different way to look at it. So if this helps you, then awesome. Entropy is a thermodynamic function that describes the number of arrangements. Okay. So how many different ways could I teach you guys in here? A lot of different ways. So could I change the entropy of this room dynamically every single day? I could put you in pods. I can put you in pairs. I can put you in groups of 6 to 8. I could change rows. I could turn you sideways, left, back, front. So it's the different possible combinations of how things can be arranged that are available to a system existing in a given state. Entropy is closely related to probability. So if you're a statistics fan, which I am not, this is why I don't like this method, this is all running through with statistics. The key concept is that the more ways a particular state can be achieved, the greater the likelihood of finding that state. So here in English, nature spontaneously proceeds towards states that have the highest probabilities of existing. Now let me kind of give you a little picture to help in your brain figure that out. Of the two particular pictures, what is nature probably going to select? All the molecules on one side, none on the other, or mixed? Mixed. Now, in terms of disorder, which one has more disorder in it? The one on the bottom one, okay? Because there's more area that it overturns. And so nature's going to prefer this. If there were 100 people in here, where would you probably want to go? Out the door. Because things always transition from high to low. Well, what's going on over here in the top picture in the left bulb? There's a lot of stuff going on, right? These molecules are going to try to escape as best as possible. So when you turn it, they can escape. They're going to evenly disperse themselves out. Okay. So let us use the simple example as an ideal gas expanding into an evacuated bulb. Now, first of all, this term evacuated, what does evacuated mean? There's nothing, no, there's no air in there. Like it's empty space. There's nothing in that at all. Okay. Why is this process thermodynamically favorable? Now, what does it mean by thermodynamically favorable? Spontaneous. Will those molecules naturally on their own move to the other side? No, we're not going to have to force them at all. Simple. The driving force is probability, because there are more ways of having the gas evenly spread throughout the container than there are ways for it to be in any other possible state. The gas disperses, attaining uniform distribution. That's what it's going to try to do. The consequences are dramatic for large number of molecules. For example, how many possible microstates exist for a sample of 4 ideal gas molecules and 2 bulbs of equal volume? So again, look how many different possible states you can have. How many different states is that? 16. Again, if you take statistics, this is something that would make a lot of this make sense. And if you look at that, there is no 2 bulbs the exact same. Okay? So what is nature going to do? You love this? Oh, yeah. This is going to do whatever it takes possible to try to figure out how to get it in the most disarranged way as possible. Okay? All right, we'll stop there for today, and we'll pick up with entropy tomorrow.